So in section 2.3, we're going to talk about angles of rotation. And we had mentioned before that in geometry, when we talked about an angle, we were always stuck representing only angles between 0 and 180 degrees, right? Because we defined an angle measure this way as opposed to this way. Today we're going to extend that definition of a angle and with the following. So if we talk about a standard form or standard position angle, we're going to take an XY axis Hi, John. And we're going to embed our angle into the XY axis. So we're going to put the vertex of our angle at the origin, and one arm of our angle is going to lie on the positive x-axis. We're going to call that part the initial side. And then we're going to take the other arm of our angle, where the pivot is kind of at the origin, and we're going to allow that to rotate counterclockwise. So if I want like a 190 degree angle, I'd start here and I'd rotate, I'd go like 90 degrees, 180 degrees, and like 10 degrees more. Would give us like a 190 degree angle. This side over here is called the terminal side. So using this definition, we can even now define things that are bigger than 360 degrees. So if you take the same idea here and say we want to draw a 400 degree angle. So again, draw my initial side, and then we'll rotate. So 90, 180, 270, 360, and like 60 more makes that 400 degree angle. Is everybody okay with what we're doing? Remember, every quadrant is 90 degrees because the quadrants are perpendicular, right? The x and y axis are perpendicular to one another, so each quadrant is like 90 degrees. So I'm just kind of counting as I'm spinning around. Everybody okay with that notion? Now we can also define a negative angle in this way. So the positive angles are rotating counterclockwise. If I want to draw a negative angle, say like negative 100 degrees, instead of rotating counterclockwise, I'm going to rotate clockwise. So like negative 90 and then like negative 10 more. Makes like a negative 100 degree angle. Is everybody okay with that idea? So now we've come up with a way to define an angle of any size, right? Can be as big as we want, can be as small as we want. Any number is now an okay number for an angle measurement, right? Everybody's cool with that? Before we were stuck between 0 and 180 degrees. Now we can define an angle of any size we'd like, whether positive or negative. So this is a big deal, right? That's part of what we're trying to do is, build out these definitions for sine, cosine, and tangent so we can really take sine, cosine, or tangent of any angle measure. We've now defined a way to describe an angle of any size, which is the first step on that road. Tyler?
So how do you, like when you go beyond 360 degrees, how do you visually tell the difference between like that angle versus like a 45 degree?
Great. So this is the next concept. So we're going to talk about something now called coterminal angles, and I think this will answer your question. So let's say we have, for example, the angles 60 degrees and then 420 degrees. So we'll draw the 60-degree angle here. And again, for something like that, I'm just kind of estimating, right? Basically, I just want to draw something that looks like it's more than halfway. 45 is halfway, so just a little bit past halfway is fine, right? We're not going to be too picky with that. We're not measuring anything. We're just kind of eyeballing it. We good there? And then the 420 degree, so 90, 90, well, that would be 180, 270, 360, and then 60 more puts us in the same spot, right? So a situation like this where the terminal side of both angles is in the same location is what we're going to call coterminal. And it turns out for our purposes in trigonometry that if we take like sine, cosine, tangent, etc. of these angles, they're going to give us the same value. So, Tyler, to answer your question, it doesn't really matter because angles like this that are have the same terminal side, kind of we can treat the same way. Does that feel okay? But that's exactly the next natural question you should be thinking about. It's like, okay, does it matter like whether I took one spin or two spins or just like less than a full spin? If the terminal side is in the same spot, does it matter? And the answer is no, not really. So one of the questions that we'll be looking to ask here initially anyways is finding coterminal angles. So let's say we want to find two angles that are coterminal to 47 degrees. So I'm going to draw a little bit of a picture to kind of illustrate what's going on. It's not necessary to draw the picture, but I think kind of initially as we're still learning on kind of how to do this and getting comfortable with the definitions, the picture kind of helps justify what it is that we're doing. But it's not a necessary part of kind of answering this question. But I want to do it just so we're kind of visualizing things the right way. So let's start by just drawing our 47-degree angle. Everybody's okay with that? So something coterminal to this, I'm going to go to the 47, and then I would do like another spin around, right? Everybody's okay with that idea? So what did we do here? We did 47, and then a full spin is how far? 360. So that would be, 407. So I did the 47 to get the coterminal in the same spot, and did a full spin to end up back at the exact same spot. Everybody's okay there? And if I wanted another coterminal angle, well, I do the 47, I do one spin, and then I'll do another spin. So here I have two spins. So like 767. Everybody's okay there? Yeah, Emilio?
During that process, can you just take 407 and then add 360 to that?
Yeah, so that's the same idea, right? Is this part right here is still 407. So you could think about certainly taking your previous answer and adding another 360 for sure. And is there any limit to the number of times you could do this? No, you could just keep doing this forever and you keep generating a new coterminal angle. What if instead of continuing rotating counterclockwise, what if we had decided to rotate or do our spin the other direction? Would have that made any difference?
Yes.
Well, so let's say, again, we do our up to 47, but this time we spin that way, or spun that way, I guess is the past tense. Since I spun clockwise, instead of adding 360 degrees, I should be subtracting 360 degrees. So that should be 313, negative 313. So you could do it that way as well, right? You could add 360 or subtract 360. They're both going to give you coterminals. And just like you can add 360 as many times as you want, you could subtract 360 as many times as you want. They're still going to keep generating coterminal angles over and over and over again. We feel okay with that? How would this change if instead we had a radian measure? An angle that's given in radians rather than degrees. Here we won't bother to draw the picture since we've kind of established what the procedure is. It'd be the same idea, right? As I still would want to add or subtract 360. The question is, what's 360 degrees in radians? Well, let's just convert 360 degrees in radians by multiplying by pi over 180. So that's just going to be 2 pi. So I'm just going to add or subtract 2 pi. Everybody's okay with that? So to add pi over 3 plus 2 pi, I need to make a common denominator. The common denominator in this question would surely just be 3. So I'm going to multiply 2 pi over 1 by 3 over 3. That's going to give me pi over 3 plus 6 pi over 3, which will come out to be 7 pi over 3. Everybody okay on that? let's say that to find our second coterminal angle, instead of adding, let's subtract this time, just, you know, for grins. You could add 2 pi again to your previous answer, as Emilio suggested, or we could subtract from the original. Either is okay. And just like before, to subtract these two fractions, I need to make a common denominator. That common denominator is definitely going to be 3. Should be easy to see that. And then pi minus 6 pi is negative 5 pi over 3. Everybody okay with this idea of coterminal? Fairly easy idea, but this is a big breakthrough for us. You know, we've extended that definition of of how we measure an angle quite substantially, and now can handle a lot of situations that we couldn't have handled in our geometry class. Just as a little reminder here, if we struggle with the adding and subtracting fractions, or if it's just like, hey, this is too time consuming for me, you can always do this kind of thing on the calculator if you just leave off the pi's. So I can do, instead of pi over 3, I'll just do 1 over 3. And instead of 2 pi, I'll just add 2. And then if I hit the math and fraction button, that gives me 7/3, and I can just add the pi back in at the end. Just as a way to kind of shortcut having to do all this adding a fraction arithmetic, which can be kind of tedious if you have to do it a bunch of times. But your calculator can handle all that kind of stuff for you if you know how to ask it nicely. Everybody okay with this? Okay. Now comes the big building block here. So this is the big section, the one where we're going to extend out our definitions now of sine, cosine, and tangent. So let's just say we have some angle of rotation here. I'm just going to call that angle theta. Now I'm going to pick a point on that terminal side. Doesn't matter kind of where, I'm just going to arbitrarily pick that point to be there. That point is going to have coordinates x and y. So far, so good. Nothing weird yet. I'm going to drop a perpendicular from that point. I'll call that point L. Now, what do you notice that we have here? A right triangle. Everybody see that? Okay. Now, the side length for side OL is going to be what? It's going to be x, right? Because to get to that point P, we go x over. And then the other side length of my triangle, PL, is going to be what length? Y, because then we go y up. That's how we plot a point. Everybody's okay there? And then what's the radius then, or I'm sorry, the length for OP? How would we find the length for OP? X squared, it'd be the square root of x squared plus y squared, right? Just using the Pythagorean theorem. Is everybody okay with that? We know the hypotenuse squared is equal to the sum of the legs squared. I'm going to just abbreviate that with the letter R. Okay. So no matter how we draw our angle of rotation, we can do that. We can build this kind of a triangle, right? And basically all the measurements would remain the same, right? They would, I mean, the numbers would change depending on the point P we chose. But whatever the point P is, like the X and Y, we just fill in the values to this situation, right? Okay. So using this drawing then, I can now define my sine, cosine, and tangent in terms of x, y, and r. So sine theta is opposite over hypotenuse, right? So it's really the same thing as y over r. In this side, the opposite side is the y, the adjacent side is the x, and the hypotenuse is the r. Everybody's cool with that? So cosine should be x over r. Tangent should be y over x. Cosecant should be r over y. Secant should be r over x, and cotangent should be x over y. And this is pretty good. We'll improve on this here just in a few minutes, but let's live here in this world for a moment and do a couple of examples. So let's say that our point P is this negative 3, 4. So that's some point on the terminal side of angle theta. And we want to find the 6 trig ratios for that theta. Tyler?
For like the things you wrote out, the bottom right one, is that COT?
Yes, that's cotangent, COT. Maria?
What's the fourth word?
Terminal?
Yeah.
You're welcome. So obviously we know what x and y is, right? X is negative 3 and y is 4. We still need to find r though. this case, that's just going to be 5. Everybody happy there? Okay. So sine is y over r. Cosine is x over r. Tangent is y over x. Cosecant is r over y. Secant is r over x. And cotangent is x over y. So far, so good? Pretty easy, right? Now you have new definitions for how we define sine, cosine, and tangent, but they're really just kind of related to our other definition, right? So worst case scenario, you could draw your point 3,4 and just kind of build out your triangle and just go from there. Is that okay with you guys? Because again, once you've drawn that triangle, we call that a reference triangle, by the way. When you draw that triangle based on your standard form angle like that. Notice when I drew this triangle, I'm always drawing the perpendicular back down to the x-axis. Right? This one that I always draw is always back to the x. But if you do that, and if you don't remember like, oh, it's y over r and x over r or whatever, you can go back to SOHCAHTOA after you've drawn your picture, right? What if we wanted to do the same thing, but instead of giving you a point on the angle, we just give you a specific angle measure? Well, let's draw the picture. So 150 degrees, let's see, so that's 90 and like 60 more. So it'll put me kind of over here, right? So far, so good? Okay. We'll make ourselves a right triangle. Actually, let's use a different color. What does this angle measure have to be down here? 30. Everybody's good with y 30 degrees? I know a straight line is 180. We did 150 of it. There's 30 degrees left. Everybody's okay with that? So really what we have here is a 30, 60, 90 triangle, right? So let's fill in the side lengths for the 30, 60, 90 triangle. So those are x. And then this side is going to be negative because we're on the left side of the x-axis, right? Or I should say, the left side of the x-axis, correct? It was going to be kind of a confusing way of talking. Turn left here, right? That's like the worst direction giving possible. It's like, wait, what? Which way am I turning? I meant turn left here, correct? You guys get what I mean? And just try not to be confusing. Okay, so this guy down here is always going to be our theta. And now we've built our reference triangle. So we can go ahead and just list down our values for sine, cosine, and tangent. And the like, just by doing our regular old SOHCAHTOA stuff, right? So sine would be x over 2x, or just 1/2. Cosine would be negative x root 3 over 2x, or just negative root 3 over 2. Tangent would be x over negative x root 3, or when we rationalize the denominators, negative square root 3 over 3. Cosecant would be 2x over x, or just 2. Secant would be 2x over negative x root 3, which simplifies down to negative 2 root 3 over 3. Hi, Lily. And then cotangent would be negative x root 3 over x, or just negative root 3. Is everybody okay with that? Yes, of course. So the takeaway here is any of these angle in our reference triangle that's going to be a multiple of 30, 60, or 45, we can find the exact values for sine, cosine, tangent, etc. using these 30, 60, 90, and 45, 45, 90 triangles. So we're going to do that, and in doing so, create what's called the unit circle. But we're going to make one little addition to this. So before we get going and doing that, I just want to point out a couple of things that'll be important to what we're doing. So we have, actually, let's use okay. So what we're going to do is we're going to fix a point that is always 1 unit from the origin. So that point P that we make when we make our reference triangle is always just going to be 1 unit from the origin. We're going to fix that distance. And as we rotate that point along, the shape that it's going to make is going to be a circle, right? If we have a point with a fixed distance from the origin, and we rotate that point, it's just going to make a circle. Everybody's okay with that idea? Because the radius of this circle is 1, we're going to call this a unit circle. And what we're going to do is we're going to define the points on the unit circle, the x and y coordinates, that correspond to these angles that we can find the values for, or the exact values for, using our 30, 60, 90, and 45, 45, 90 triangles. So for example, let's say that we're talking about this point here. So that point would be the angle 225. Is everybody okay with that? So if I remember, for a 45, 40, 90, 45, 45, 90 triangle, the side length ratios are this, correct? However, the radius of this triangle needs to be the same as that, or I'm sorry, the hypotenuse of that triangle needs to be the same as the radius for this circle. So it needs to be 1 unit long. Everybody's okay with that? So the value for x then that I need here would be 1 over the square root of 2. Right? Because 1 over the square root of 2 times the square root of 2 just gives us 1. Everybody's on board with that? So both the sides of this right triangle have to correspond to 1 over the square root of 2. So remember that this side is like my x coordinate, and this side is like my y coordinate. Is everybody okay there? And since this point is located in the 3rd quadrant, I know that the x coordinate is negative, and the y-coordinate is also negative. All right, because we've gone to the left and then down to get to that point, P. So when we complete our unit circle, it's going to look like this. So I've dropped this into OneNote for you, so you don't, obviously, there's no need to copy this. Okay, we'll come back and do some examples with it in a moment. I'm also going to dump it into the notes here so we can use it to refer to some things here in a minute. So there's one other big takeaway, though, from the unit circle. So if I do this and say I wanted to do sine of this 225 degrees over here, if I do opposite over hypotenuse, I get that, right? And anytime I'm using a unit circle, R is going to be 1. So what does this takeaway become? If sine was y over r, sine theta, and r is 1, well, sine is just the y-coordinate. Or if cosine theta, x over r, and r is just 1, cosine theta is just going to be the x-coordinate. And similarly with cosecant, r over y just becomes 1 over y. And secant theta, r over x, becomes 1 over x. So let's say we want to use the unit circle to evaluate, let's say sine of 120 degrees. And then let's say tangent of 5 pi over 4. And then we'll do cosecant of 390 degrees. So if I'm going to do sine of 120, I know that's equal to the y-coordinate. So I'm going to locate 120 degrees on my unit circle, which is right here. And I'm going to pull the y-coordinate from that, and I'm done. So the sine of 120 is square root 3 over 2. Okay with that? Tan of 5 pi over 4. I'm going to go and locate 5 pi over 4 on the unit circle. So if I see that, it's right here. Tangent is y over x. So I'm going to take the y-coordinate, which is negative root 2 over 2, over the x-coordinate, which is also negative root 2 over 2. That just gives me 1. Now, for cosecant of 390, I notice that the unit circle only goes up to 360 degrees, right? So what I'm going to do is I'm going to find the angle that's coterminal to 390 degrees. I can get that, and also between 0 and 360. I can get that just by subtracting 360. So really, this is the same thing as cosecant of 30 degrees. So I'm going to go to my unit circle and find 30 degrees. And I know cosecant is 1 over y. Which is just 2. Everybody okay there? We feel okay using the unit circle to pull values? It's not too bad, right? You just find the right angle or the correct angle, and then you use your little formula to figure out which coordinate or combination of coordinates you need. Let's do one more example problem, and then we'll stop for today. So this question says we want to find sine theta if cosine theta is equal to 5 over 7 and cotangent theta is negative. All right, so let's think about what it is that we're trying to do. So if I draw a picture here, cosine is x over r, right? So either my triangle is going to be here, or my triangle would be here. Because the x-coordinate has to be positive 5. And the radius is always positive because it's a distance. Ben? Sure. So the question becomes, which one of these two triangles should I be looking at? The one in the first quadrant or the one in the second quadrant? Well, it should be the fourth quadrant, excuse me. The first or fourth. This other piece of information is going to tell me. Cotangent, I remember, is x over r. And I know already that the x is positive because x is 5. So that tells me the y is negative, right? Because the only way a fraction is negative is either the numerator or the denominator is negative, but not both. So that tells me that this is the triangle that I'm looking for. So far, so good? So what I'm going to do then is I'm going to start right away by putting a negative sign here on this side because I know it has to be negative because we're in the fourth quadrant. The y-coordinate must be negative. And then I'm just going to use the Pythagorean theorem to solve for that y-coordinate. So subtracting 25 from both sides. And then we'll square root both sides. I remember I can simplify a radical by breaking it up into like a perfect square and then some other stuff. So 24 is 4 times 6. So that would be 2 root 6. And now that I have my other side, I can write sine theta is opposite over hypotenuse. Cool with that? Okay. So that'll be that for chapter 2. So we can now finish the chapter 2 problem set, 42 through 60. And I'd also have a, where's that at? Have a worksheet to practice this second, or this unit, or oops. Section 4 content that I'm going to drop in also. So this is the other part of the homework here, is this worksheet 1. So it's just practice using the unit circle. And then some of these problems just like that last example problem.